In this video, I'm going to spend some time talking about the action potential. This is probably one of the more difficult concepts to grasp in biopsychology. It's well worth spending some time because it's fundamental to how the brain works. Without understanding action potentials, you can't really understand the rest of the course. After you watch this video, I want you to be able to define what an action potential is and then explain why it's important. You'll be able to, you need to be able to explain the steps involved in triggering it as well as generating the action potential. If we manipulate the environment, I want you to be able to predict the effect that'll have on both the initiation and generation of the action potential. From last video, we talked up to this point. The neuron is at rest. So we've got leak channels, we got sodium potassium pumps, different concentrations. When you sort of let everything settle down and nothing is going on, we have the resting membrane potential of minus 70 millivolts. It means the inside, again, is a little bit more negative than the outside. Just to refresh your memory real quickly, a potential is just a change, the separation of charge in space. If we decrease that separation, that's called a depolarization. Okay. And we do that by reducing the separation of charge by letting ions move. So here we are, back at rest again. Cell is just hanging out, doing nothing. Something is going to excite the cell. And right now I leave that something vague. It can be a lot of things. In this particular example, it could be that glutamate, which is a neurotransmitter, we'll talk about more later, may open an ion channel for sodium. If we open an ion channel for sodium, sodium's going to come into the cell. So if we bring positive charges in, that makes the inside of the cell more positive. It's the same thing as less negative. So in this particular case, we'd go from minus 70 millivolts to say minus 65 millivolts. And you know that that's a depolarization. I'll explain why in a minute. It won't make sense to you right now. But a depolarization is excitation. Okay. So in this case, this will happen, for example, on the dendrites. So on a dendrite, at a connection with another neuron, a neurotransmitter will be released. That's going to open an ion channel, and sodium's going to come into the cell. And that will depolarize the cell. So in that case, we go from, say, minus 70 to minus 60. Now, a couple things I just want to talk briefly about. Here we have, for example, the cell. I've got the separation of charge across the membrane. We're at minus 70 millivolts. Basically, if we decrease that separation of charge, and there's a couple ways we can do that, we're going to change the membrane potential. If I bring positive charges in, I'm going to make the inside less negative, more positive. So we're getting less separation of charge, right? So the number's going to go down. The inside will still be more negative. Okay, so we'll get that depolarization. Now it's important to think about how these ions move into the cell. They can't just cross the membrane by themselves. They need help. And as you know, we have ion channels for that. So ion channels are protein tunnels that basically let ions flow into the cell. There's three broad classes of ion channels I'm going to talk about right now. we have leak channels. And so these are always open. And we talked about these in terms of potassium. So we have potassium leak channels. There's no sodium leak channels. Okay, it's just potassium. That's going to allow sodium to flow. Allow potassium to flow. Which way does the potassium flow? It's going to go down its concentration gradient, right? Normally, the concentration is higher inside than out, so potassium will flow out through these channels. There are other kinds of channels, though, and we're going to talk about those in this lecture and then some later. There's something called a neurotransmitter or a ligand-gated channel. So for the next two types of channel, I'm going to talk about gating. Gating basically means what opens it. So here we're talking about neurotransmitter gated or ligand gated. So a ligand is basically just any chemical that binds to a receptor. That might not make a whole lot of sense now. We'll explain that more as we go. So in the case of this ion channel that's neurotransmitter or ligand gated, neurotransmitter is going to bind to the channel and open it. So in the previous example, I talked about glutamate. Glutamate is a neurotransmitter released by one neuron that's going to bind to neurotransmitter gated ion channels and open them. We'll get into the details later especially, but one of the glutamate receptors is called the AMPA receptor. This is a sodium ion channel. So when glutamate binds to it, it's going to open that channel and sodium will flow in. There's literally hundreds of different ion channels with different neurotransmitters. Just know the concept right now. Gating means what opens it. If it's neurotransmitter gated, when neurotransmitter binds to it, the ion channel opens up and the ions can flow. Some will be sodium channels, some potassium, some chloride, some even calcium channels. Okay, so there's a lot of these. We'll talk specifics down the road. For now, just know what neurotransmitter gated means. The other kind that's going to be important for us to talk about are voltage gated. So I already told you that gating is what opens it. Here, voltage gated means that when the membrane potential hits a certain value, it's going to open the channel. So one of the things you have to remember is that these ion channels are all proteins. An ion channel has to be a specific shape or it won't work. It's got to form a tunnel. If for some reason it is turned or changes shape, it won't work. So with a voltage gated, normally the protein is in the membrane, but its shape is such that ions can't flow through it. When the membrane potential reaches a certain level, it changes the shape of the protein. When it changes the shape of that protein, now the tunnel's open. Okay? So in the case of a neurotransmitter gated, right, it's the binding of the neurotransmitter that changes the shape. In terms of a voltage gated, it's the membrane potential that changes the shape. So these are the three basic types of channels that we're going to talk about. Here we are at rest again. We're going to get the influx of some positive charges into the cell. As I said, if we do AMPA receptors, those are neurotransmitter or ligand gated sodium channels. So that's going to be a protein here that's normally closed. When glutamate binds to it, it's going to open it, and these positive charges then can flow into the cell. As long as the cell is open, we're going to get the flow of ions into the cell. When that neurotransmitter goes away, the channels will close. Okay. Now, one thing I told you before was to remember, where am I? The action potential is triggered at the axon hillock. This is a special part of the axon, right near where it touches the cell body. Okay, so this is key. This is where what we're going to talk about mostly occurs, where it begins. These are going to be on the dendrites. Okay, so what'll end up happening is this AMPA receptor will open up, sodium comes in, I get a depolarization here. Now remember, I'm in the dendrites. This will have a small effect on the axon hillock. Remember, if I've got the dendrites way up there, right, my axon hillock is here. So if this is going to depolarize my membrane here, it will have an effect, but it'll be a small effect on the axon hillock. Remember though, we have about 10,000 connections per neuron. So if each one of these has a small effect on the membrane potential here, they all add up to have a large effect. All right, so we're at minus 70 millivolts. Things come in and we get a depolarization to say minus 60 millivolts. And that's just a small depolarization. Now, I mentioned voltage-gated ion channels. So here's a diagram basically summarizing quickly what we need to know. We're going to start with them closed. Okay, so again, here would be the membrane, right? The cell membrane. We've got outside. We've got inside. Normally, in this case, the voltage-gated channel is going to be closed. Ions can't flow. Okay, so here, the membrane potential will be minus 70 millivolts. Let's say we get a little excitation. We go to minus 60 millivolts. It's not enough of a change for the shape of the channel to change. Let's say, though, we keep going and we get to something like, say, minus 55 millivolts. In this particular case, that change in the membrane potential is large enough that now the channel opens. When it opens up now, ions are going to be able to flow. Now, we're going from a closed, stable complex, changing the membrane potential, and when it opens, ions flow. That's going to further change the membrane potential. So what ends up happening is, although they open up, they're on a timer, essentially. They don't stay open very long. It's not particularly stable. So once they open, the timer starts. Ions flow through. When the timer goes off, then they close. They'll be inactive. There's two mechanisms where they can be inactive. One is we can actually clog. So it's open, but because another protein's in the way, ions can't flow in. We can also be completely closed, where this channel closes and we kind of reset. Okay, so voltage-gated ion channels basically follow this model. There will be a potential at which they open up. This is called threshold. So when the membrane potential reaches threshold, these channels open up. They stay open for a short period of time, at which time they become inactive. Okay, so there's actually going to be three states here. Closed and ready, open, and then closed and what I'll call refractory. So closed and refractory is a time where they can't open, where ions won't be able to flow. Okay, so during the refractory period, even if our membrane potential is above threshold, this won't work. Okay, so we start closed and ready. We open up. After our timer goes off, we stop allowing the flow of ions. Ions don't flow. We're in the refractory period. The membrane potential can't open this and let ions flow. After a short time, we get reset and we go back to closed and ready. Okay, so when we have closed and refractory, they call this inactive. So the three states of a voltage-gated ion channel: closed and ready, open, and inactive. There are many different kinds of voltage-gated channels. You need to be specific. So when you're talking about this particular channel, you always have to say voltage-gated sodium channel. Okay? Voltage-gated channel is incorrect. Sodium channel is incorrect. You got to say the whole thing. Voltage-gated sodium channels. This is just another diagram showing exactly what I showed you before. At resting membrane potential, the channel's closed. Ions can't flow. In response to a depolarization, you hear the nerve impulse, the generation of the action potential. The membrane potential allows for a change in shape. The channel opens and sodium flows in. After a short period of time, this is going to move and clog it. At this point, the channel's open, right? The membrane potential may still be above what opened it, above threshold. But because we're clogged, nothing can happen. That's what we call the inactivated state. Over time, as the membrane potential goes back to the resting membrane potential, things kind of calm down. This is going to leave, this will close, and we go back to the beginning. All right, just another cartoon showing this again. You can look through this on your own, but this is how we think voltage-gated sodium channels work. The opening is rapid. The depolarization of the membrane that leads to is also rapid. That resetting, though, is relatively slow. All right, so we were sitting at rest. We had a depolarization. Remember, we went from minus 70 to minus 60 because those AMPA channels opened up. If we keep going, though, and we hit minus 55 millivolts, now what happens? At threshold, minus 55 millivolts, those voltage-gated sodium channels open up and allow a ton of sodium to come into the cell. Remember, before we had gone minus 70 to minus 60 to threshold. So we're at minus 55 millivolts. Now, what will happen to the membrane potential as tons of sodium comes in? We're adding lots and lots of positive charges. That's making the inside much less negative. So instead of minus 55, right, the membrane potential will change to 30, to minus 20, to 0. And in fact, so much sodium comes in that we're going to go all the way up to plus 30. What that means now is our separation of charge is 30 millivolts. Now, because of the sign, though, the inside has a slight excess of positive charges. Now remember, this only occurs in this local area. The first place on the neuron where you see these voltage-gated sodium channels is the axon hillock. Okay, so this change we're talking about begins at the axon hillock. So you remember I got the whole neuron, right? And here's the axon. Here's the axon hillock. Okay, I got my 10,000 synapses coming in. If the membrane potential here at the axon hillock reaches threshold, voltage-gated sodium channels will open up. There are no voltage-gated sodium channels on the dendrites or the cell body. They start on the axon hillock and are only on the axon. That's important. So when we reach minus 55, wherever there's voltage-gated sodium channels here at the axon hillock, but not over here, they'll open up and sodium will come in and give me a nice big depolarization of the membrane. And so I may go to, say, minus 5. And as I said, sodium keeps coming in. I get enough that actually the polarity is reversed. So instead of being negative, now the inside is a little bit positive. How long is sodium going to flow in? It's essentially going to flow in until it reaches equilibrium, when the force of diffusion and the electrostatic force kind of balance the flow, or those voltage-gated sodium channels close. Either one of those will stop the flow. As I mentioned, we're going to have electrostatic and the force of diffusion working to drive sodium in. Early on, inside is negative. So while the inside of the cell is still negatively charged, we're attracting sodium in. But I also just told you at some point it becomes positive. So then that electrostatic force will actually reverse and repel sodium. All right, so sodium, as I said, is going to flow in until equilibrium is reached or the channels close. Once the channels close, sodium's going to stop flowing. All right. There's a time, though, where separate voltage-gated potassium channels open. Okay, so these are the same principle of the voltage-gated sodium channel. They're normally closed. When we reach a certain potential, they open up and potassium flows out. So there's a time when sodium is flowing in and potassium is flowing out at the same time. It turns out in this case, I've got this trying to depolarize to make it more positive. This, as the potassium leaves, right, when I lose positive charges, I'm making the inside more negative. So I've got something trying to drive me to a positive membrane potential and something trying to make me more negative. So what happens to the membrane potential? Obviously, it depends on which of these is faster. It turns out that this flow of sodium is much faster than potassium, so sodium wins. When both of these are open, we're going to get a depolarization still. But eventually what's going to happen is that those sodium channels close. I wrote close, but really it's become inactive. Okay, so they become inactive. Now the flow of sodium stops. Potassium is flowing out unopposed. And as potassium flows out, we're making the inside less positive, which is the same thing as more negative. Okay, so if we were at plus 30, the inside becomes less positive. So instead of plus 30, we go to plus 20. Keep on going to 0. So much potassium comes out that we actually end up getting a slight hyperpolarization. We go all the way to minus 75 millivolts. Now, this phase where we go from all that sodium in, the inside's positive, we're going to call repolarization. Okay, so we talked about depolarization. Depolarization is actually going from rest to positive. So in this case, say plus 30 millivolts. Once we do that, now we have to reset the cell. Okay, that's what repolarization is going to be. So again, we were at plus 30, then maybe we're at plus 10, and eventually we're going to get to minus 70. And actually the potassium channels stay open a little bit too long. So instead of stopping at minus 70 millivolts, we actually get a little overshoot. We go down to minus 75 millivolts. Now the potassium, again, is going to flow until the channels close or it reaches equilibrium. And so the potassium channels at minus 75 millivolts close. Now we got a little bit of excess potassium. That is going to diffuse away. Okay, and so remember, I got my negative, I've got some positive charges here, right? So the inside is a little more negative. If I get rid of these, if they diffuse away, they won't affect the membrane potential here anymore. Okay, and so that's exactly what happens. That potassium diffuses a long way away. Astrocytes, for example, can pick it up, but as it goes away, it's not going to affect my membrane potential here. We pull those out of the equation. The separation of charge is smaller, right? If we're getting rid of positive charges, that difference is less. So we go from minus 75 back to the resting membrane potential of minus 70 millivolts. I know, that's a lot. Take a breath if you want. I'm going to go through it again using this diagram, though. Here on the y-axis, we'll have the membrane potential. On the x-axis, we'll have time. This is a great diagram because it goes through all the key events that you need to know and understand. So here we're at rest, minus 70 millivolts. We're going to get some excitation. Here it's called a depolarizing stimulus. It can be many things. I used the AMPA receptors as the example, but there's many other things it can be. So we get a depolarization. Now, if the membrane at the axon hillock, remember, we're talking about here, the axon hillock. We're not talking about the whole neuron, just here. If the membrane potential there hits threshold, then those voltage-gated sodium channels open. When those open, sodium comes into the cell. Okay, so that rapid entry of sodium into the cell is going to depolarize my cell. Up in this area is actually where the potassium channels open. Okay, so this is a little different than what's on this diagram. But in this region right here, those voltage-gated potassium channels open. So remember, sodium is flowing in, potassium's flowing out. Sodium wins though, so we're still going to get a depolarization. Up here at the peak, the sodium channels close. And really, I mean voltage-gated sodium channels, right? So when those close, sodium no longer flows out, no longer flows into the cell. Now that flow of potassium is unopposed. So as we lose positive charges, we lose potassium, we're going to get repolarization. Okay, so basically from here to here is depolarization. From here to about here is repolarization. When we get this little excess, that's hyperpolarization. So from here all the way until we get back to rest is a hyperpolarization stage. So there's three stages. the depolarization stage, the repolarization stage, and then the hyperpolarization stage. All right, so our sodium channels have closed, potassium is flowing out now. As that occurs, we get that repolarization. I mentioned that they leave, they stay open just a little bit too long, so we get a excess potassium leaving that leads to a hyperpolarization. Eventually those close. When those close, potassium's going to diffuse away, and we go back to resting membrane potential. So as I said, the stages of the action potential are depolarization, repolarization, and then that hyperpolarization. Another diagram, another way to look at it. Again, x-axis is our membrane potential in millivolts. Here we have time. We've got rest. Now we've got our depolarization, our excitatory stimulus. The reason it's called excitation, right, is the action potential is a signal. So when the neuron has to send information, it generates an action potential. This is excitation. Okay, so anything that moves us toward threshold makes it more likely that we're going to fire an action potential. That's why we call it excitation. All right, so we reach here, threshold, voltage gated sodium channels open, sodium rushes in. Somewhere along here, potassium, voltage gated potassium channels open, potassium leaves. As you know though, the flow of sodium is greater. So the sodium channels, we're still going to get depolarization because sodium is entering the cell. At this point, they become inactive. Sodium's no longer flowing. Potassium, however, is still flowing out. So as that goes, we get that repolarization. Once we hit our original resting membrane potential, we actually get a little bit of a hyperpolarization because those channels are open too long. The potassium channels, though, eventually are going to close. After they close, potassium no longer flows. We're going to get diffusion. As that occurs, we return to rest. Okay, so again, these are good diagrams for you to work through. I would strongly recommend starting with a blank piece of paper and drawing these out, and then just explaining to yourself as you go what's happening. Just walk yourself through it. That's all it takes, but you got to do that. Okay, so this massive depolarization is the action potential, also known as the nerve impulse. This is basically the signal that carries information. Okay, so when a sensory neuron detects something, it's going to generate action potentials. That's part of this signaling mechanism. If we block action potentials, I'll talk about pain. So pain is a problem. If someone has pain in their hand from, say, arthritis or something, those neurons, those sensory neurons that detect painful stimuli, are going to be excited. They'll generate action potentials. Those action potentials are going to go along the axon into the spinal cord. That information is going to get transmitted to another neuron. Eventually, that info is going to get up to your brain where you perceive the pain. If we block action potentials, then that information never makes it to the brain. The brain doesn't know anything's going on. The receptors will still be stimulated. They'll still try to generate action potentials. But if we treat with a drug, and a lot of local anesthetics do this, that block action potentials, Now that signal won't get through. Okay, so this is what it carries information. It's an important signal. Without an action potential, the information doesn't get from one place to another. So again, the action potential, why it's important. Hopefully you can explain that. All those different steps that I went through, I want you to be able to explain and reproduce. I'm going to test you on this, where we'll manipulate the neuron in its environment and predict how that's going to affect the action potential.